Hey class, welcome to another digital lecture. So we're starting today by looking at something called the chain rule. This is going to be a way that we can help figure out derivatives of things like this. Like if we wanted to find the derivative of cosine x cubed, that's a cubed. Or if we wanted to find the derivative of the square root of t to the fourth plus 1. Because we know how to find the derivative of cosine now. We know how to find x cubed. We know how to find t to the fourth plus 1. We know how to find the square root of a function. But we haven't learned how to do compositions of those functions. And that's the thing in question right now. Because as you can see from the first one, this is a composition of the function cosine x with the function x cubed. So this is our theorem. It's called the chain rule. So if f and g, two functions, are differentiable, then the composition, which can be written as f composed g of x, which is the same thing as just f of g of x, that is also differentiable. And the derivative of the composition f of g of x is given by f prime of g of x times g prime of x. That is our chain rule. Might seem a little strange right now. After the proof, I'm going to show a few examples to try and give it some context. So let's have a look first at the proof. So, proof. I'm going to write it in terms of a little bit different functions. I'm going to write it like this. So we want to show that y of x of t prime equals y prime of x times x prime of t. And to do this, we're going to revisit our earlier understanding of the derivative. So let's imagine back like that first day of class that we had. Let's say we have a graph of x versus t, and there's some curve that we want to figure out the derivative for. And so if you remember, what we did is we started with one point on the curve, drew another point, drew the secant line between the 2 points, and we thought about how the fact of if we took the second point on the secant line and started moving it closer and closer and closer to the first, we would get the derivative. So that's, that was our approach back before. And we had a different way of notating things, but basically we knew that this slope of this secant line, so if you realize that this slope of the secant line is just given by the rise over the run. In this case, since x is on my vertical and t is on my horizontal, it'll be a rise of delta x and a run of delta t. Okay, so, and we saw earlier that the derivative x prime of t could be found by taking the limit of the slope of the secant. So, sorry, my pen's acting a little weird. May have to use this side. Okay, so we found that the limit as delta t goes to 0 of the slope of the secant. Instead of writing all the symbols that we used to write, I can just write very simply delta x over delta t. That's the derivative of x with respect to t. I'm not going to draw the graph, but you can actually do the same thing if you had a graph of y versus x. Okay. So now here's where some clever things are going to come out. I'm going to draw in the tangent line, so the actual x prime of that value. So let's say we've got down here that point that we were considering, that's at a t subscript 0, so t naught, if you will. And if you drew in the tangent line, I'll do it in green on mine, the tangent line looks something like that. And actually, let me fix this a little bit, just to make it totally clear. How can I fix this better? So, trying to give my tangent line a little bit of slope kind of makes it a bad tangent line. Okay, well that's not good. Okay, yeah, you have to fix it, the small part of the graph. Actually, okay, excuse the technical difficulties. I'm going to redraw the graph real quick. So we had this x versus t, some curve, initial point, final point, secant line, delta x, delta t. Okay, this is our point of interest, t naught. Okay, now I'll draw on the derivative. This is the slope of this is the tangent line, which has some slope to it. This is the derivative line, at last. Takes a while. Okay, so we can actually do some analysis here. If I draw a dashed line over, just totally horizontal from my first point, t naught, and I draw a vertical line down from my point here, I can see that I can find two distances. There is this distance in blue. That distance in blue is like the rise, in reference to the rise over run, of my tangent line slope. So let me try and write this out for us. This is a bit to figure out. If we know that slope equals rise over run, then I could just say that rise is equal to slope times run. Okay, I'll show you why that's going to be useful in just a second. I can take another color and color in the rest of this distance up here, and I'll just call this epsilon. Crazy colors. I'm just going to call this one epsilon 1. Okay. All of this to say I'm just trying to find a way to rewrite delta x in terms of other variables. So I can say that delta x is partially equal to the blue part, which is, again, it's the rise, which equals the slope of my tangent line, x prime of t naught, times the run, which is delta t, plus that epsilon 1 also times delta t. The reason I gave a delta t to the epsilon 1 is because as I move that second point on my secant line closer and closer to the first point, that epsilon 1 distance will shrink. And I don't have the graph drawn, but I could do an analogous thing for my delta y equation. It would be written like so. Okay? Now both of those equations can be factored. So the first one you can take out a delta t. The second one you can take out a delta x. Okay, so a little bit of algebra. You can see that my first equation, the delta y equation, has a delta x right here. Well, the whole first line was a delta x. Well, so that means I can take my delta y equation and say that delta y just equals all of the delta x stuff, which is delta t, oh boy. Delta t times x prime of t naught plus epsilon 1 times y prime of x naught plus epsilon 2. Okay, almost there. If I divide both sides by delta t, I'll get delta y over delta t equals x prime of t naught plus epsilon 1 times y prime of x naught plus epsilon 2. The next step comes by seeing that, well, I'm looking for the derivative of y with respect to t. That's what I was trying to get ultimately in my first derivative part of the proof. I'm trying to take the derivative of y of x of t. So it's a derivative with respect to t. So now to do that, it's as simple as taking the limit of delta y over delta t. So y prime with respect to t is the limit as delta t goes to 0 of all of this stuff. Now the clever thing here is realizing that as delta t goes to 0, both of those epsilon values end up going to 0 as well. And if you just look at the graph, the reason is the closer that that second point on the secant line gets to the point where you're taking the tangent line at, the closer the slope of the secant line gets to the slope of the tangent line, and the more those epsilon values will shrink. Therefore, you can say that all of this, when evaluated, is just x prime of t. Well, I guess I should label everything. It's y prime of t naught, x prime of t naught times y prime of x naught And generally then, what that would mean is that the derivative of y of x of t is simply equal to y prime of x of t times x prime of t. And that's the end of it. So a long explanation to get us to this final chain rule. Before I show you any examples, I just want to point out the fact that this chain rule can also be written as you wanted the derivative of y with respect to t, and it ends up equaling the derivative of y with respect to x times the derivative of x with respect to t. As you can see from this here is y prime of x, that's dy dx, and this thing here is x prime of t, this is dx dt. Neat thing about that notation is that you see two fractions where the dx's actually cancel out, so to speak, to leave you with dy dt. So you can see that both sides are equal. We won't necessarily use this much now, but it becomes really valuable in higher level math and physics courses. Okay, so now some examples of problems to try and help you see how this all comes into play. Okay, so let's take that first example I gave you. Y equals cosine of x cubed. Find dy dx. Okay, so dy dx. According to the chain rule, I take the derivative of the outside function. So, if you look back, it says it's y prime of x of t. So the inside stays the same, right? So before you're taking the derivative of y of x of t. Now it's just y prime with still the same inside. So if you look at cosine x cubed, the outside is a cosine function. So the derivative of cosine is just negative sine. The inside stays the same. And now the second part is simply what's the derivative of the inside? Well, the inside is x cubed, so the derivative is 3x squared. Final answer is minus 3x squared times sine x cubed. Okay, example 2. Take this derivative. Okay, so you should see that your outside function is the square root. Derivative of a square root is 1/2 times all the same stuff on the inside to the negative 1/2. Then you just multiply it by the derivative of the inside, 4t cubed. So you get a final answer here of 2t cubed times t to the 4th plus 1 to the minus 1/2. Okay. Let's do a couple more. If y equals tangent of x over x plus 1, find y prime of x. Alright. This would be a good time to pause the video and see if you can figure it out on your own. But I'm going to show the solution now. Okay, so the outside function is tangent, so the derivative of tangent is secant squared. Inside stays the same. Times the derivative of the inside. So here's it's a quotient, so you gotta use the quotient rule. So it'll be low d high minus high d low over low squared. Okay, so the top you can see is x plus 1 minus x. So you'll just get 1 over x plus 1 squared. Sorry, I only wrote x is secant of x over x plus 1. So you could say your final answer would be secant squared of x over x plus 1 over x plus 1 squared. Alright. So 3 more practice examples. Find the derivatives. Okay. So first function, y of x equals all of this. That should be to negative 1/3. B is y equals e to the cosine t. And then the last problem is find the derivative of square root 1 plus square root x squared plus 1. That'll be a double chain rule problem. So I recommend pause the video, try these 3, and then check my solutions. So this first one, y prime of x equals minus 1/3. All of the inside stays the same. To the minus 4/3 times 2x plus 7. Second one, dy dt, derivative of e to the whatever, it's just e to the whatever, times the derivative of the whatever, which will be a negative sine t. So you can just write negative e to the cosine t sine t. Last one's a little involved. So multiple chain rules. So first, you've got a square root. So that means 1/2 times everything on the inside. To the negative 1/2. Now times the derivative of the stuff on the inside. Well, that's 0 plus 1/2, because you got a square root, all the stuff on the inside, to the negative 1/2, times the derivative of the inside, okay? And then now you can simplify it a little bit. So you'll note that the 2 over here and the 1/2 cancel out, and you'll be left with a net 1/2 x times x squared plus 1 to the minus 1/2 times 1 plus root x squared plus 1 to the minus 1/2. So kind of messy solution, but that's it. Okay, and I'm actually going to break up the lectures into 2. So this is the first part, and then access the second video for the rest. But C block, you can find the homework that was posted for G block on Friday that goes along with this lesson.